When we apply TTQ to train our networks, we realize that after training, the ternary matrices did not have any obvious structure and resembled random ternary matrices. So here we have two matrices, one of which is random and the other one was trained by TTQ. Can you tell the difference between them? On the left, we have our trained ternary matrix, and on the right we have a random ternary matrix. So in our opinion, they look quite similar, and we use this as the motivation of our approach. In our algorithm, we only create random ternary matrices once before training. The ternary assignments, -1, 0, and +1, remain constant throughout training. Moreover, scaling factors are learned by preceding and subsequent layers, so we do not learn them ourselves. In our case, sparsity is controlled by a constant threshold t, but any other ternarization scheme would work. Effectively, in our approach, each NIR only computes the difference of activation sums, which may be scaled by a batch norm layer, which is then passed through a nonlinearity such as ReLU.
Let's check our results on large-scale speech recognition using Librispeech.
For our floating point baseline, we used QuartzNet with 15 blocks and 5 sub-blocks. As originally proposed, the number of channels varies within each block. In the table, we can see that our baseline achieves 3.98% word error rate on devclean and 3.83% word error rate on testclean. Moreover, we can observe that it has around 90 million floating point parameters. For our simplified variant, we would like to note that QuartzNet's letter blocks contain most of the parameters. Hence, we propose to ternarize blocks 10 to 15, which reduces the number of trainable floating point weights to half. Even with around 50% of the parameters being now sparse random ternary, we only sacrifice around 1% word error rate on testclean and devclean. Using random ternary matrices has several benefits. First, it allows for faster training, since no weights need to be learned or updated. Also, it allows for faster on-chip inference, since no multiplications are required and sparse operations are in play. Finally, we can achieve higher compression rates, since no weights need to be stored. They can simply be generated on the fly. We thank you for being interested in our talk, and hopefully you'll consider using random ternary matrices in the future to further compact existing network designs.